Today we have Jay Haskamp presenting a special case study that looks at the differences between aerial, mobile, and traditional survey workflows. And so without any further ado, I'll let Jay take it away from here.
Okay, thanks, Dylan. Hopefully you can all see my screen and hear me okay. Just want to thank everybody for attending today and welcome you here. So a couple quick things before we get started. For those of you that are attending and watching this, you should have an option to ask a question, and I believe there's also a chat box option. So how we want to handle this is I have Dylan in the background kind of monitoring things. I also have Nathan Stevenson out of our office in Arvada, Colorado with us today as well. These two guys are kind of our residential experts on the mobile and the aerial LIDAR. So I have them here to kind of help out with questions. And if you have a quick question you just want to ask one of them and get answer right away, feel free to put that into the chat window as they can see and monitor that. Otherwise, we will be taking questions throughout the presentation, but we'll be waiting till the end of the presentation to go through them. So if you put the questions that you may have into the questions box, Dylan and Nathan can't see those, only I can see those, so we'll cover those at the end. So again, if you want something kind of quick and easy, put it in the chat. Otherwise, if you want to wait till the end with a more complicated question or something like that, feel free to put it in the questions box and we'll address that when we're done. So today we're going to talk about a project that we did here where we're comparing various things, I guess what you could put it with, aerial data, so photogrammetry and aerial LIDAR, and then mobile LIDAR, and kind of comparing it to traditional survey workflows to look at several things versus time to collect data, time to process, the quality of the data, and things like that. So hopefully you guys will find this beneficial, and hopefully there'll be some good information in here for you. So a little bit about myself. Here I am on the screen here. If you haven't met me, I'm in Frontier Precision in our St. Cloud, Minnesota office. I've been around for a while, so I feel like I know most of our customer base, but I know there's people outside of our territory in here as well. But I've been with Frontier for 12 years, and I've been in the surveying engineering kind of industry since 2002. So I have some background in that industry before I started here. And so let's move on to our project here. So a little background on the scope of this project, or what we're trying to accomplish here. So first was to go out and perform a topographic survey of a roadway using various different technologies. And the first thing we needed to do to kind of have a fair comparison is we needed to put out a solid control network that we can tie all of our data to, we can register all of our data to. So having a solid control network, I feel, was kind of the biggest key component to this whole project. So we spent a lot of time making sure we had that right. Then we went out and conducted a survey with a robotic total station to basically create road cross sections, line work, and a surface model. And the topographic survey with the total station was going to be kind of our benchmark to compare everything to. Because when we look at traditional survey methods, a total station is typically seen as being a more accurate method than say using GPS. So we wanted to really just make sure that all of our baseline comparison data was really tight and accurate, and it was a good data set to use to compare everything to. Then we went out and conducted additional surveys. So we did a cross-section survey using GNSS off of a base station. We did a photogrammetry survey. We did an aerial LIDAR survey, and then we did a mobile LIDAR survey. And with all those different surveys that we did, we used the data to produce the same line work and the same surface models. So we had kind of an apples to apples comparison of everything. With the data, we went and compared items such as, how much time does it take to collect the data? How much time does it take to produce the data? What's the quality of the data if we compare, the quality of the point cloud or the quality of the images, things like that. The data accuracy and just the efficiency. So how fast can we, get this done from start to finish? And then we just wanted to produce some hopefully thorough and honest findings for everybody based on what we found. So the goal of this isn't to say use this or use that, because they all kind of have their time and place. It's just more or less to get everything in the same playing field here and just produce information for you guys to look at and make some determinations on. So what is our goal for doing all of this? Obviously, we worked really hard on this. I spent a lot of time on this, had a lot of help. First and foremost, we just want to determine how these technologies measure up to traditional methods. They're kind of this new cutting edge emerging technology. Everybody's talking about it, but there's not a lot of information on just how this stuff all compares. So we wanted to definitely determine that. And then we've never really thoroughly tested these technologies and compared them to how we currently do things. We'll get the mobile scanner here at the office and we'll say, oh, let's go out and scan something, and it looks great, but we never really sit down and really thoroughly take a look at it and just to see, like, okay, what's good and what's bad about this. And we were finally able to utilize all these tools. So obviously, mobile scanners and aerial LIDARs aren't something that's always readily available. And it just kind of worked out. At one point in time, we had all of our sensors in Minnesota and just decided to kind of jump on the opportunity. And that's kind of how this thing ballooned up from there. So we want to answer some questions. First one would be, can we be more efficient in how we do things? Are there more cost-effective methods of collecting and producing data with these sensors? Are they accurate enough for what we're trying to do or the situation that we're working in? And then are there any additional hurdles or things that we will encounter with these technologies? And we definitely had a few bumps in the road, and that's valuable information as well, because it's kind of those things that you don't really know until you get into it, that you're going to have to deal with. So what sensors did we use for kind of our baseline data set? We used the Trimble S7. It was just a 3-second, pretty standard robot. We tried to use tools that we figure most of our customers would use on a daily basis. So a 3-second S7 with the TSC7, running the latest version of Axis at the time, which was 2019.1. The GNSS survey, we used a Trimble R10-2. This was pre-ProPoint, so we always have a discussion on, okay, what's the next iteration or the next level of this, but I'd like to try it again with like an R12 with ProPoint. But for what we did, we had an R10-2, TSC7, and again, Access 2019. So the same controller and software were used for both surveys. Then when we move on to the other sensors, for photogrammetry, we used a DJI M200. Version 2 was the airframe. And then on there, we used a PPK system from Cloud Geomatics. So Cloud is somebody that I've known Rob for a little while now. We've had a good relationship with Cloud, and they make a solid system. So we put that to the test, and that PPK system integrates on the M200 with a Sony RX1 R2 camera. So we had a custom gimbal, and we're able to run a really nice Sony camera on that photogrammetry system. So that's what we used for that survey. The aerial LIDAR was a DJI M600. And for that LIDAR sensor, we used the YellowScan VX20. We'll dive more into that in a minute, but that's the kind of our aerial LIDAR sensor that we use here at Frontier. And then I had to throw a little picture of Dylan in there since he was kind of my moderator today. But this was when we were setting up our MX9. So it's the dual laser MX9. This was actually a picture from the day that we did the scan. So method to our madness. What are we trying to do here, and why are we doing what we're doing? So, I've done a lot of research on this. We've looked at a lot of different, different option, or I don't want to say case studies, but different studies or things people have done and published online. And it seems like anybody can kind of make this as easy as they want. A lot of times you see just kind of a bare bones test, and people don't really want to dive into it and spend a lot of time on it. But we wanted to make sure that, if we were going to put the time in on this, we wanted to really work in a real world scenario that's going to have various hurdles and challenges that are part of it. We didn't go out kind of looking for problems, but we wanted to put ourselves in a situation that, say, a customer of ours would be in. So a couple of things that we took into consideration was, do we do a curved road or a straight road? So you can kind of see the snippet from the aerial on the screen here. This is the road we did in St. Cloud. It's actually right by our office here. And we chose to work on a curved road because that poses various challenges, because when you start, running out line work along a linear road, it's easy to just kind of push lines out, at, 100-foot intervals or whatever, and just kind of make adjustments and go. But when you get into a curved road, it just kind of makes things a little bit more difficult when you're trying to, say, look at point cloud cross sections and things like that. So we wanted to make sure that, we worked on a nice curvy road, and this road is pretty much just one continuous curve. We also wanted to work in a project that had curb and gutter versus a rural road. A lot of these roads that we see are just long straight roads with a paved surface and a shoulder and a ditch. We really were interested in the curb and gutter information, as well as you can see on the image, there's a lot of parking lot entrances and things like that coming into that road that, that we would have to deal with. So that's something that we deliberately wanted to look at. And then probably the biggest one that can be kind of a pain when processing this data is we wanted to work in a local coordinate system. In Minnesota here, where I'm located, every one of our counties within our state has its own coordinate system. So this was done in Stearns County. So we wanted to work in that local projection, because that's what literally 99% of people in Minnesota work in, is in a county system. Now, those of you who have any experience with LIDAR, whether it's aerial or mobile, or especially photogrammetry, know that if you're working in local sites, there's a lot of hurdles and things you got to deal with. So we knew that going into this, but we were bound and determined to kind of figure out how to make it work. We actually learned some stuff along the way, which hopefully I'll remember and share with you, that actually kind of helped us out. So this is kind of what we wanted to deal with, because we figured this would be a typical scenario. All right, so the control survey we did, just a little bit of background on this. We knew we needed a solid control network. Hopefully you can see the image on there. This is the control network we used. It was based off of a previous network that we had in place that was established from 2 nearby harm points. So we moved to this new office in about 1.5 years ago. And one of the first things I did was I set a bunch of control around our facility here. And where we're at, we're lucky enough we have more control than we could ever need. We have harm points all over the place. So we tied our office control network into 2 harm points. We ran through it with a digital level, and we have a really solid network here. So if you look on the screen, you can see over here is point number 1. Point number 1 is kind of the common point. So what I mean by that is our control network around our office. Point number 1 is kind of our anchor point. That's what we use for our vertical benchmark when we ran our level loop and things like that. So this network for this project is anchored off of point number 1, which is kind of our benchmark. So we wanted to make sure that these tied together, more just for redundancy if we needed to tie back into that network. But we wanted to make sure that we were using something that we knew was good. And then we also have this WTPK point up here. That's actually our base station on our building, which is part of the Minnesota VRS network. And the reason why it was important to incorporate that point in is because that's the base station we processed all of our data off of. So we had to make sure that that was, adjusted as part of our network. So we established our control network. We figured out what we wanted to do. The primary control was established just using a static survey. So we did a static session on all the points, processed the baselines, did a network adjustment, and got all of our horizontal positions locked down. And then we went out to go level through it. We didn't have a digital level at the time, but we took an SX10 out, which is a 1-second robot. And then we used the Level Me module within Access and ran a trig level through all of our control. And I'll show you, we're actually very pleased with the results that we received off of that. And then once our primary control was all adjusted and leveled through, we used the SX10 and set out some additional control, because we knew doing the total station survey, we would need some more points out there. So we made sure that we used measure rounds for everything, and we tied everything in. So we had, mean turned angles and things like that. So here's just a picture of of what our control targets looked like on the road. So we went out and we set PK nails along the road in pairs. So there's one on either side. I think we had 4 pairs. And then we painted these white chevrons with the PK nails at the tip of the chevron. And I actually ordered some of the reflective glass beads from Amazon, and we put those in the paint to make them more reflective. And then we painted some black around the outside just to try to get some more contrast to make them pop. So this is one of the R10s we used for the control survey, running the static session on one of our points. And then this is the just some of the data. So you can see here's our baseline processing report of our control, and then these are the adjusted grid coordinates running it through the network adjustment. And then again, you can see our level. Our raw misclosure was actually like 3/10,000ths of a foot, so it was pretty much flat. So very minimal adjustment run through there, but this was all put together to establish our network. So once that was done, we moved on to the cross-section survey. So again, we wanted to use something that we knew our customers would be using. So again, it's just that S7 with the MT1000 prism. So it's just a standard multi-track prism. And then we used our control network, and we only did station setups. We wanted to avoid resection. So every setup was over a known point and backsighting a known point. And then for added redundancy, or maybe we're just a little too anal about this stuff, but we did a compensator calibration at every setup just to make sure that we took any leveling issues out of play. And then all the topography or cross-section measurements we took were done in phase 1 and phase 2. And the reason we did that was just for extra redundancy and accuracy, so we didn't have any randomly bad shots in there that if we shot phase 1 and then phase 2 and got an out of tolerance message, we could look at it and say, okay, is it within what we want it to be, or do we want to discard it and do it over? So the cross sections we took were roughly at 100-foot intervals, and then the measurements we took were from back of curb to back of curb. So we didn't really want to focus on utilities or signs or lights or trees. We're more just worried about road information. So we just went from back of curb to back of curb. The GNSS survey, you can see on the pictures, this was a fun day. We didn't collect the data in this order. We kind of collected it as time permitted, and the GNSS survey, we got caught by surprise. Typical fall in Minnesota, it's sunny and 40, 50 degrees one day, and then we get 2 feet of snow the next day. So we had to improvise, but we used an R10 Model 2 TSC7 running Trimble Access. So we could have ran VRS because we have a VRS network here in Minnesota, but just because we were processing all of our other sensors off of our base station, we decided that we wanted to do a full RTK survey and get our corrections from our base station as well, so everything was consistent. So we found our control targets on the road, dug them out, found our PK nails and did a calibration. So we were on the same network or control as our targets were. And then we did cross sections about every 30 feet. So you can see we got caught with the snow. That's me with the rod in the background. And some of you may know who Tony is, one of our other AGEs here in St. Cloud. He was there with his shovel and his ice chisel and helping me. You can kind of see the picture on the lower right-hand corner there. We were chiseling out the curb and gutter to make sure we got down to the right surfaces. But again, because of this, we only went back a curb to back a curb, but we feel we got the necessary data for what we needed to do there. Photogrammetry survey. So again, use the M200 with the Clow 7700 PPK system. The Sony camera, it's a 42 megapixel camera, full frame sensor. It's a great camera for photogrammetry. It was just a single grid flight. 75 meters was the height we flew at, with a 70% and a 75% overlap. So the PPK was processed off of our Waite Park course site on the building, and the data was tied to our ground control points that we set. On the ground, we could see the targets. You can actually kind of see in the image here, they might be small, but you can see our target pairs here, here. We actually had point number 1 here, here, and here. And then we processed the data two ways, actually. We processed the data locally on the computer. We processed it in Pix4D, and then we processed it up in the cloud using Dell Air AI, Dell Air's cloud-based platform, because we wanted to see just kind of two different ways we had the data. It didn't hurt to run it through a different variation. And then the data was processed in our local projection and our vertical datum. The aerial LIDAR survey, again, that was the M600 with the yellow scan VX20, which has a Regal sensor on it. You can see in the map there, we basically had two flight lines. We flew kind of the outer edge of the road and then the inner edge of the road. The GPS and the IMU was processed in POSPAC, again, off of the Waite Park base station. And then the LAS files that we created were with Yellowscan's Cloud Station software. So that's their kind of their LAS processing software. And then this is where we kind of ran into our first hurdle. So we had trouble exporting out the data in our local coordinate system. So we tried, there's some options in there to create custom projections or custom exports. We didn't spend a lot of time on it, but we never really got it to work. We were doing something wrong. But we found out that TBC, just kind of playing around, TBC actually solved the problem for us. So what we found out is that TBC has the ability to reproject point clouds, which is a pretty powerful tool. So the way we kind of got around this was we exported out our LAS files in Minnesota State Plane, and then we created a TBC project in Minnesota State Plane and brought them in. And then all we had to do was simply go to our project settings and change the coordinate system to our local site, and TBC reprojected and adjusted our point cloud. We brought our control file in, it fell right in where it should, and then we geo-referenced the point cloud to our control in TBC. So TBC certainly saved the day for us there. And then lastly, the mobile LiDAR survey. So this was the MX9, dual lasers, 360-degree camera as the side cameras, the rear camera. We'll talk about that a little bit later. But for those of you that have mobile mapping experience with the MX9, you have to kind of warm up and calibrate the IMU and the GNSS. So Dylan took it out on a nearby highway and just drove around for 10 minutes or so and got things all kind of oriented and ready to go. And then when we actually had him drive this road, he drove, I think it was actually 18 miles an hour is what we figured it out to be, but right around 20 miles an hour, and collected 1,600 feet of data in just under a minute. So you can see on the screen there, that's the whole mobile mapping project. The ends are cut off a little bit, but he got all that in under a minute. We brought that data in and processed the trajectory and the IMU, GNSS, all of that into POSPAC. And then you bring all that data into TBC, and using TBC's mobile mapping module, we processed everything in TBC, created the LAS files and so on. All right, so let's talk about data collection times. So try to explain a little bit what we're looking at here. I wanted to put this on graphs so you can kind of see what we have going on here. But we have our mobile LiDAR, our aerial LiDAR, photogrammetry, and then our GNSS topography survey. So the question is how long did it take to capture all this data? So we have two aspects of this. We have the physical time it took to collect the data, which is what is in white. But we also have the total time, which is in red. So that includes kind of the other things that aren't part of the data collection. So to break this down, we'll start at the bottom and work up. The topography survey with the GNSS took us 1 hour and 31 minutes. So with that, we were doing 2-second topo shots. We weren't doing rapid points. That included calibrating to our control targets on site, and then doing our cross sections from back of curb to back of curb, and then any extra detail on the parking lot entrances and things like that. This does not include any time shoveling snow and chiseling ice. They actually were able to stay ahead of me, so I didn't have to wait for them. So this is just purely purely data collection time. The photogrammetry portion of this, the actual data capture time was only 8 minutes. So it was an 8-minute flight. But there was also 22 minutes of, mission planning, setting it up, tearing it down, things like that. So the total time for the photogrammetry flight was about 30 minutes. The aerial LiDAR, The flight itself was 15 minutes. So we fly a little bit lower and a little bit slower to get, the density that we were looking for. So the flight was a little bit longer, but it had a little bit more of a setup time. And, honestly, part of that is when we got the system, nothing was put together. So we had to mount the antenna, we had to mount the bracketing and everything like that. So that probably took a little bit longer than normal, but the setup time was about an hour and 12 minutes. So the total time for the aerial LIDAR flight or aerial LIDAR survey was an hour and 27 minutes. And then lastly, with the MX9, you can see the actual data capture. I just rounded it up to 1 minute, but we had an hour and 11 minutes of setup time. So that was, mounting the bracketing and the mounting on the vehicle, mounting the MX9 on that, taking it out on the highway and driving it around to do the calibration, and then tearing it down and putting it all back. So the total amount of time there for the MX9 was an hour and 12 minutes. So, what do we learn here? We look at this, and except for the photogrammetry portion of it, everything was pretty much even. It was pretty even. So we're kind of trying to digest this and figure out, okay, what are we getting from this? Like, what are we understanding here? And if you look at it, this was only a 1,600 foot section of road. So if we look at it, there's really no reason to choose, say, an MX9 over GNSS if you're just talking about time. Now, there's other things we have to consider there, but these things were all pretty even. So we had to ask ourselves, it's like, well, what do we need to do to determine how, if this is more beneficial one way or the other? So we figured we need to project this out. So we looked at 1,600 feet. What does it take to do a mile, or what does it take to do 2.5 miles, or what does it take to do 5 miles? So we sat down and we started crunching numbers to figure out, as we get on these longer projects, how these things kind of start to set themselves apart from the others. So here's the slide to show that. So there's a lot going on here, but the information in white is what it took us at 1,600 feet. The information in red is the time to do a mile. The information in blue is the time to do 2.5 miles, and the information in green is the time to do 5 miles. We had to think of each thing kind of individually to determine what that time would be. So to start with the GNSS down on the bottom, that was pretty easy. We know, okay, it took us an hour and 31 minutes to collect this data by hand. If we're in a scenario with a road similar to what we're doing, we're likely going to have cross streets. We're likely going to have the same amount of parking lot entrances and the same type of data to collect. So there was just simple math. So with the amount of time it took us to do 1,600 feet, we calculated to do a mile would be about 5 hours. To do 2.5 miles would be about 12.5 hours. And to do 5 miles would be about 25 hours to do this all by hand. Then we move up to the M200 with the photogrammetry. And when we got into the photogrammetry part of this, we actually selected a similar road and actually did flight plans to get hard data from the flight plan software as to times that it would take to do this. But the other thing we had to consider here was, you're not going to get all these flights or these surveys done in one flight. So what you see here is like this little 2F in parentheses. That means that it would take 2 flights to accomplish that. So the other thing we had to think about is, okay, if I'm going to do this in 2 flights, I have to factor in a battery change. So how long does that take? So I talked to a couple of our drone guys, and we kind of came to the consensus that to bring a drone in, land it, swap the battery, take it back off, and restart where you left off we'll just figure on average about 10 minutes. So for every flight change, we factored in 10 minutes in there for a battery swap. So for the M200 to do 1,600 feet, we're at 30 minutes. Now, when we push that out to a mile, we have to do 2 flights to make that happen. So we have 1 battery change. So technically, to collect data in a mile, we're at 40 minutes, but we had to throw 10 minutes in for a battery change. The other thing I should mention here too is for the longer setups, we're not adding any additional time from this slide from the install mount, because you're only going to do that once, right? You're only going to set it up once, you plan once, and tear down once. So these numbers are consistent they're not getting any bigger. All we're looking at is strictly the collection times as we're projecting this out for different distances. The only thing that we did not include in here for any of the aerial stuff would be time moving from one place to the other, because you have variables with visual line of sight and maybe having to move down the road a mile so you can see the next section. We didn't take any of that into consideration. It was strictly the data collection, so just keep that in mind. So with the M200 out at 2.5 miles, now we're at about an hour and a half with 3 flights, and when we get out to 5 miles, we're out about 2 hours and 40 minutes, and that's with 5 battery changes. Now we're thinking, okay, well, who's going to fly 5 miles with an M200, for photogrammetry? You may have somebody that'll do it, but once you're starting to push that distance out, you may be looking into more of a fixed wing solution. So we figured we better also, we didn't collect data with it, but we better figure out, just for a fixed wing. So we have the UX11 as one of our platforms that we use. So we figured we better check that as well. So the values with the UX11 came out, 28 minutes, hour and 37 minutes in one flight, 58 minutes. This was right on the bubble of doing it, of doing it in one flight. But we figured, you might have wind, you might have things like that. So we broke it into 2. And then 5 miles would be about an hour and 20 minutes with 2 flights. So you have a comparison between a rotor solution and a fixed wing solution here. The aerial LIDAR, obviously going to take a little bit longer, right? Because we're going to fly it lower and we're going to probably fly it a lot slower than photogrammetry. So 1,600 feet, we had our hour and 27 minutes. You can see as we push out into a mile, we're about an hour and 50 with 2 flights. 2.5 miles, about 2 hours and 40 minutes with 3 flights. And then 5 miles are about 4.5 hours with 7 flights. So that would be, 6 battery changes. And then the mobile LIDAR, we thought, well, we did it at 18 miles an hour. Let's figure it out at 30 miles an hour. Really didn't make that much of a difference. But you can see we're at an hour 12 versus an hour and 11 minutes. At 1 mile, we're at an hour 15 versus an hour 13. 2.5 miles, an hour 20 versus an hour 16. And then at 5 miles, an hour 28. I keep clicking here, sorry. An hour 28 versus an hour 21. So, if we look at it from a perspective of the longest case scenario, 5 miles, we're at about an hour and a half or less with mobile. We're at about 4.5 hours with aerial LIDAR. We're anywhere from an hour and 20 to 2 hours and 40, depending upon what we used for photogrammetry. And then for a GNSS survey, doing it by hand, we're at about 25 hours. So that's kind of how everything is stacking up time-wise. All right, so we had the data collected. We had all of our information on, what's involved with it and how long it takes. Now we need to check the data and look it over and see how everything kind of worked out when we validate the data. So we decided mostly to focus on the vertical results because that seems to be what everybody's interested in, and that's the easiest to look at. So we were like, okay, what are we going to use for our pass fail? What are we going to call good? What are we going to call not good? And initially we just came up with this number of 2 centimeters, and there really wasn't any scientific reasoning behind this. It was just like, oh, well, the RTK spec for vertical is 2 centimeters. Let's just use that because people would maybe use GPS. So that's where we started. So about 6/700ths of a foot. And then I attended a presentation from a gentleman with the Minnesota DOT's photogrammetry division. And in Minnesota DOT, the photogrammetry people, they process the drone data, but they also process the aerial and mobile LIDAR data. And he gave a presentation about what they do at MnDOT. And I had a good conversation with him afterwards. And he gave me this table, and this is what MnDOT uses. So this is MnDOT's standards for mobile and aerial LIDAR and UAS. And these are based off of, ASPRS formulas and things like that. So you can see 95% confidence and not to exceed. So this is kind of what they're looking for here. So I thought that's probably a better benchmark for us to use. So in the end, what we decided to do was compare all of our data, not only to this 2 centimeter threshold, but we decided we're also going to compare it at 1/10 of a foot and 2/10 of a foot, just to see, because For some projects, a tenth may be good enough. You know, maybe some projects you need 2 centimeters. Maybe some projects 2/10 is good enough. So wanted to make sure we just kind of covered it all. So that was what we decided on for validating our data. And then how do we do that? So we isolated the point clouds down to just the roadway. And then what we did was we extracted out the ground to remove any, you know, people or bicycles or whatever. And then we created full resolution surface models. So typically, you know, if you're making a surface model of a road with LIDAR, you're probably going to sample it down to every couple of feet or half a foot or whatever. But we wanted to just compare raw data. We didn't want sampling to have an effect on this. So we just went full on resolution, made surface models, and then used that for our comparison. And then what we did is we compared those surface models to the control points that we set for targets along the road. And then we also compared them to our total station cross sections to see how the surface models hit with our kind of our benchmark baseline data. So what we did is we compared those using the points to surface tool in TBC, and then we determined how many checks fell within the 2 centimeters, the 1/10, or the 2/10 of a foot. The other thing we had to factor in here was the data processing time. So for the GPS data or GNSS data, the processing time took me 2 hours and 51 minutes. So this is bringing the data into TBC, processing the line work, making sure that we're detailing all the curves and the entrances so we have a nice, you know, arc through all of our points as we go around the curve. You can see we have some nice curves going into the entrances, you know, making break lines and things like that, and then creating the surface model. Now, I'm sure a lot of you could probably do this a lot faster, you know, in a CAD product, excuse me, like Civil 3D or something like that. But again, just in the terms of consistency, I wanted to do everything in Trimble Business Center. So we're, you know, everything's being done in the same place. So this took us 2 hours and 51 minutes. And then looking at the data, you know, we all know what it looks like. So there's nothing really fancy or to show here, but just some information. We end up with about 622 measurements outside, and then varying levels of horizontal and vertical precision, but at the 95% confidence level, the vast majority of them were fixed under 1/10 of a foot. Now, taking that surface model that we created from the GNSS cross sections, we compared it to the control points that we had on the road. So there's a couple different things going on here. First, the points that fell outside of our 2 centimeter, we have marked here with a little red star, and then the points that fell outside of 1/10 of a foot are marked with the blue star. So you can see, as an example, points 3, 4, and 6 were over 1/10, and then points 7 and 10 were within 1/10 but over the 2 centimeter mark. And then the other distinction I want to make here is these 3 points that are highlighted in yellow. Those are actually points that we used in our calibration in the field. So we used 0.5, which is, where's 0.5? Over here. We used 0.2, which is over here. And we used 0.8, which is over here. And then we also factored in 0.16 and some other stuff here. But for our control points, these 3 points, obviously they hit really well because they were part of our calibration. I just wanted for each one of these to just cut a quick cross section just so you can kind of see what that looks like. And every one of these cross sections you'll see is at the exact same spot on the road. What we wanted to do here when we looked at the cross section data was I picked a spot where we had a GPS cross section that was in the exact same spot as the total station cross section. So what we actually did when we did the total station and the GPS cross sections is I had drawn a map and I had drawn lines along the alignment, like cross section lines, and we did our cross sections on those lines to try to keep that consistent. So we weren't comparing a total station cross section to a GNSS cross section that were 30 feet away, that they're right on top of each other. So the green is a total station surface and the red is the GNSS. So you can see it matches up very well. Now this slide is when we take our surface model from our GNSS cross sections and we run a comparison to our total station cross section measurements. So we're not comparing 2 surfaces, we're comparing the physical total station measurements that we took to the GNSS surface, okay? So what we have here is points that fall outside of 2 centimeters are going to be marked in red. So out of our 79 checks that we had, 58 of them fell within 2 centimeters. So 73% of our checks fell within 2 centimeters. 87% of our checks, or 69 out of 79, fell within a tenth. And all but one, we had one kind of outlier up here, which is really high. I have to look at what happened there, but that one fell outside of the 2/10. So 99% of our GNSS measurements were within 2/10 of our baseline data. Now moving on to photogrammetry, looking at the processing times, there's a lot of stuff here, so I'll try to explain this best I can because there's a couple different ways we had to look at this as well. So total time, start to finish, doing everything all in was about 8 hours and 18 minutes. However, I do have this 5 hours and 40 minutes behind it because there's parts of this that we didn't necessarily have to include in here. So what I mean by that is first we have to process the PPK data and process the photogrammetry. So this includes, processing the PPK from the cloud system, bringing it into the software and running the, the initial orientation on it, constraining it to the ground control, re-optimizing it, and then producing a full resolution point cloud. So we decided to go with the full res point cloud just to have the density match up with what we would be seeing with the LIDAR sensor. So that whole process took 3 hours and 5 minutes. And then there was optional processing that you don't have to do. I wanted to do it for this just to have it, but we created a full resolution orthomosaic. That process took right over 2.5 hours. Now, again, that's not a requirement for what we're trying to do, but that's just an additional part of this. Now, if we look at the TBC side of it, we thought, okay, so are people going to process in TBC or are they going to take it to a third party? So we figured we better check both. So to bring the data into TBC, classify the point cloud down to different regions, and then export it out to a third party, that process took about 10 minutes. But if we wanted to do the full processing in TBC, which would be segmenting out the road, cutting our cross sections, creating our points along the curb and our line work, and making our surface model to basically produce what we did with the GNSS, that took 2 hours and 25 minutes. So that's why there's different times here. One is to do everything, and then one is to just get it out to third party. Now, there's a couple caveats you got to also keep in mind when working with GNSS, or with photogrammetry data, is that not all the processing time is required by someone physically being at the computer. A lot of that is just pushing the button and letting the computer go. And then you also have the power of your computer. Obviously, I have a processing computer that's going to run through data a lot faster than my laptop. So those are always things you have to also consider. And then this is just a screen snap of the data from the local photogrammetry processing around the curb and gutter here. You can see my points and my line work that we push through. And then I want you to kind of keep in mind this dark area here as we go through these, and we can see how this kind of evolves here. Looking at it from cloud, oh, I'm sorry, I'm not there yet. So a couple more slides on this. So we had 117 photos that we processed locally. So here's just an example of one of the Sony images, a very crisp image, high resolution camera. Our Pix4D report, everything looked pretty good there for our processing. We created a full resolution point cloud. So we had about 1 point per pixel. It gave us 163 million points. You can see looking down at the point cloud, which you see on the screen here, it looks really good. But when we threw a limit box in there and started turning it on the side, we were noticing some things that concerned us a little bit. So you can see there's plenty of detail, but now when we flip it on the side, we're looking at one of our targets here, and you can see there's a lot of noise in this data. There's a lot of kind of fuzz in the curb and the road surface. So we were interested in seeing how that was going to kind of play out through the rest of this. But the orthomosaic we got through it looked really, really good, and we were happy with that. So looking at that data and comparing it to our control points, again, the same thing, our surface model from our local photogrammetry, comparing it to the control, we had 3 points that fell outside of our 2 centimeter threshold. And then we only had 1 point that fell outside of our 1/10. So I was actually kind of surprised at how well that worked. I was happy with what we saw there. Now, when we look at that same cross section, you can look at the data kind of from a different perspective here. You can see how much fuzz and how much noise there is in there. Now, that explains some things, obviously, when we start comparing a full resolution surface model, right? There's a lot of noise here, but that can be caused by various things due to weather and lighting and camera settings and things like that. And typically, when I make a surface model of this, I'm probably going to sample it down to make that more of a a consistent surface and not so noisy. But again, we went all in full resolution. So there's what you see for the cross-section view. And then lastly, getting to this, this is the me comparing the photogrammetry surface again to those total station cross sections we took. And some of these points I have crossed out here, and I just want to explain that. What that is we took these, we collected this data at various times and various days, and it's the fall here in Minnesota. So we went through because we had some outliers, and there's different spots where there was, a pile of leaves in the gutter line or something like that. So any of those points where there's some question where there's missing data or there's stuff in the gutter of the road or debris that we have to deal with, we just threw those points out. So that's why they're crossed out. So looking at the data, 46%, so 35 out of 76 of our photogrammetry points or checks fell within our 2 centimeter threshold. If we bump that up to a 1/10, we did a little bit better. We're up to 66%, so over half. And then when we go up to 2/10, actually all but one of them with the local photogrammetry fell within 2/10. So we were pretty happy with that. Now taking that same data and pushing it through a cloud-based system, we wanted to see, okay, what's going to be different? So photogrammetry cloud-based, that process took about 45 minutes. And that was really just to upload the data. I chose to mark the ground control manually and then download the completed data when it was done. And typically that's ready, next day, same day. I think I did it in the morning and it was probably done in the evening sometime. So not a lot of work involved into getting that data up there. And for this one, using Del Air's platform, we can also use different processing engines. So we wanted to make sure we used a different processing engine to see if we got different results. So here's just kind of some pictures of their interface of the 2D and the 3D, the point cloud view on their platform. And then now looking at the data, so we had 117 photos. Once we had figured out with being able to reproject point clouds in Trimble Business Center, that made processing in here a little bit easier because their platform didn't support our local system at the time. So we just processed this in US state plane, brought the point cloud into TBC and reprojected it like we did earlier, and it worked just fine. So we created a full resolution point cloud. Again, you can see it looks really good. But what was interesting is when we took that limit box and looked at the same place, this is the same place we looked at with the other data set, as you can see there's a lot less noise in this data set. It's a lot cleaner. And I was very impressed when I saw that. And then also we got the orthomosaic and the DSM, which was all part of that online processing. Comparing that surface model from the cloud-based photogrammetry to our control, everything hit within 2 centimeters. We didn't have any outliers. Looking again at the cross section, you can see there's a lot less noise. It's a lot more consistent in terms of the noise in the data and the surface we have from our point cloud. And then looking at this same image here, again, there's different ones that had to be crossed out because it was a different day. Actually it was the same day, but I think our points where they fell within our surface model was different. I should re-say that. But looking at this, we had 62% fell within our 2 centimeter threshold. 76% fell within a 1/10, and 96% fell within 2/10. So we were better in the 2 centimeters and the 1/10 than processing it locally, but we were a little bit worse on the 2/10, which I found was kind of interesting. But again, here's what we ended up with. So what does this tell us about photogrammetry? Well, obviously it has its time and its place, no doubt. We all know that. Everybody these days seems to use it, but if it's done properly, it can definitely be accurate enough for certain situations. I maybe wouldn't use it on a hard road surface like this, but definitely for other things, certainly a great tool. There are too many variables, however, in the field and the office to have a one-size-fits-all solution. So, you have different software algorithms, as we just saw here, will provide different answers. So just keep in mind, it's up to you as a professional to determine, what's good, what's bad, what should I use. One of our recommendations that we do here is to utilize proper standard operating procedures within your company, just to make sure, you have proper training, on your sensors and your software, and everybody's consistent and doing the same thing. And then no matter what you hear, you always need ground control. Okay, you hear that a lot, survey grade this, survey grade that, no ground control this, no ground control that. You cannot validate your data if you don't have any checkpoints or any ground control to report your accuracy to. So always have something on the ground to validate your data every time you do this. Moving on to aerial LIDAR. So processing the data here took us 2 hours and 42 minutes to go all in with TBC, and 31 minutes to just get it out to third parties. So that includes, post-processing the trajectory and GPS in a Planix, creating the LAS files out of CloudStation, registering it to ground control and TBC, and exporting to third party. And then to create the line work and the surface model and things like that in TBC took about another 2 hours and 11 minutes. So start to finish about 2 hours, 42 minutes. Here's that same curve. Again, you can see my points and my line work that I drew around that curve. Hopefully you kind of start to see a little bit more definition. I don't know how this comes across on your screen, but a little bit more definition in this dark spot here. And then now analyzing the data. So we had about 10.2 million points. We didn't decide to go with color. There are cameras that you can add to this yellow scan system. We had them, we decided not to use them just because it was one of our first times flying it. We just wanted to collect data. Me personally, I very rarely use color when I process point cloud data anyways, but it's there if you need it. The data looked nice and clean. I don't know if it shows up good because it's a darker color, but this is a big tree that was overhanging, and there's plenty of data that made it through and penetrated down to the ground, which was another thing we were looking at with this sensor, which we're pretty happy with. But then another kind of hurdle or a roadblock we ran into was how we flew this flight. So this was something we didn't think about that we had to figure out how to deal with after the fact. Is when you're flying with this, with an aerial LiDAR, typically your laser is spinning perpendicular to your flight path. Well, we're flying along a curved road, so when we're making our turns, we're getting these areas of kind of dead space where the LiDAR is missing because that drone is rotating. So we freaked out a little bit, but really it wasn't that big of a deal, because for how we were processing this data in TBC, we had some tools in there where we could pretty much get by that and make it a non-issue. But again, it's just something to be aware of, so we wanted to make sure we presented on that. Looking at the yellow scan surface model and comparing it to our control data, we only had one outlier that was over 2 centimeters, and that was just it was 700, so it really wasn't that bad. So everything looked very good here from kind of what our expectations were. The only potential explanation, this is just a theory, so I'm not saying this is why, but this particular point fell in one of those areas where we didn't have, wasn't as dense as it is here. So I don't know if it had a little bit of a harder time making a road surface there or not, but that's just a theory that I have. Looking at the cross section, you can see it fits the total station cross section very, very well. There is a little bit of noise in the data, but honestly, that doesn't concern me, because again, I'm not going to make a full resolution surface model of my road. If I try to bring that into CAD, it's probably going to crash. So I'm typically going to sample that out, and that's going to take care of any of that noise or fuzz in there and still provide me a good result. You can see it fit the curb on both sides very well. So I was happy with what we saw there. And then looking at this, when we flew this, we had to throw 3 points out because I think there was some trash or something in the gutter of the road. But comparing that surface model to our total station cross-section points, we had 81% of our checks fell within 2 centimeters. So I was really surprised. 60 out of 74 were within our 2 centimeter mark. 86%, a little bit better, fell within that 10th. And then we had 3 of them that fell outside of the 2/10. So again, very, very good. Okay, lastly, moving on to mobile LiDAR. So the processing time here, start to finish, was 3 hours and 49 minutes. And then to get it out to third party was 37 minutes. So the steps involved in that were, processing the trajectory and the GPS in POSPAC, bringing it into TBC's mobile mapping module and running the point cloud generation. They have a nice mobile mapping ground control registration process that we used in there, and then classifying the point cloud into regions and exporting it out. You could bring it into, say, InfraWorks or something like that. Running through and making the line work and the curb and gutter and everything and the surface models in TBC. That took 3 hours and 12 minutes. This actually took me a little longer, and I have 2 reasons why. One was it was the first time I did it. I actually processed this data before the other ones. And then there was just so much detail. I found myself kind of getting lost in the point cloud, where I was just really trying hard to make everything perfect. And if I did it again, I probably wouldn't have to be so detail oriented, because I could still get a good product out of it. But it just took me a little bit longer because I was kind of learning in the process and just really trying to make a nice map there. Here's a screen snap of that same curve. Now, we were saying, look at these dark spots as we go through here and so on. Now you can really start to see the detail. And what those dark spots were is actually some potholes and imperfections in the road. And when you get into the mobile scan data, this is where this stuff really starts to jump out. We can even see all the seams and the cracks in the road and the manhole cover. So we're dealing now with a very high resolution data and a lot of detail. The point cloud itself was about 55.5 million points. So, again, that took just under a minute to collect. So we got a lot of data in a short amount of time. The point cloud was colorized, but you don't have to do that step. But this was by far the cleanest data set with the most detail. This is an elevation-based rendering, so you can really see those potholes in the road kind of jump out at you. And then cutting that limit box side view, you can see there's not a lot of fuzz or noise in that point cloud. It looked really nice. And I didn't show numbers for this, but one other thing I just kind of roughly checked was, without tying it to GCPs, how close did I get to this stuff? And this was definitely the closest to our control point without actually constraining it down to ground control. But we just decided to tie everything down just to make it even. And then we also had the additional imagery. So with the 360 camera, you kind of get this 360 street view. So this is one view looking back. The same thing looking forward. Here you can see is where all those imperfections in the roads were that we were looking at, is right here. We also have the forward facing and the downward facing cameras for signs and pavement inspection and things like that. So you get a lot of extra stuff with it too that you can use. Looking at the MX9 surface and comparing it to the control data, everything fell within our 2 centimeter threshold. So we didn't have anything too alarming to see there. And then looking at our cross-section view, you can see we have a really nice clean surface here of the road. And I actually think, the more I look at this, I actually think this is probably a better representation, because I can see, like the apron here and things like that. And it looks really good in the curb area as well. Looking at the MX9 surface model, comparing it to our total station cross sections, there was looks like 5 points we had to throw out because of stuff on the road, but 88% of those points, so 63 out of 72, fell within 2 centimeters. 94% fell within 1/10, and 100% of our points, so every single point, was under 2/10 that we used to check. So we're pretty happy with those results. All right, so total collection and production time. So this is a graph just putting it all in one spot. So field collection is the white blocks, the office processing is the red blocks, and this is just to basically produce a point cloud, get it off to a third-party software. GPS, 1.5 hours. Photogrammetry is 3 hours and 45 minutes. Again, keeping in mind, the computer side of this, where some computers will be faster than others and you don't have to be pushing buttons that whole time. Aerial LIDAR and the mobile LIDAR were pretty comparable, with right around the 2-hour mark, a little bit less. So everything was pretty flat across the board on the processing side. When we throw in the time to make line work and a surface model and everything there, we get a little bit higher. So the GPS cross sections, start to finish with data collection and producing, took about 4 hours and 20 minutes. Photogrammetry was about 6 hours and 10 minutes. Aerial LIDAR was about 4 hours and 10 minutes, and mobile LIDAR was about 5 hours. So again, everything was pretty consistent. So what we're finding as we do this is the office processing side of this, really to create everything start to finish, there's not a lot of an advantage one way or the other using, mobile scanning or GPS. It's all pretty much the same. So where you really have to look is in the data collection time, because we ran through this several times, and really there wasn't one thing that jumped out that was more of an advantage over the other in terms of processing the data. And then this is just a slide to put it all in one place so you can kind of see everything together. So the red towers are the 2 centimeter results, the blue towers are the 1/10 results, and the yellow towers are 2/10. So you can see, everything was pretty consistent at 2/10. We get some dips when we get into the, the 2 centimeter and the 1/10, but you can kind of see how everything fits together there just in one place. So quick summary, I know we're right up against our time here, so I want to get to questions. So GNSS, obviously a great tool for topography and cross sections. Can be time consuming in the field, however, on large projects, but typically it's the easiest in terms of usability to process and make maps from. One thing I didn't mention though is, in my mind, one of the downsides of GPS is it just still requires somebody to physically be on the road. That's one aspect that all the other systems really kind of throw out. Photogrammetry, great way to cover a large area of ground, works for great rough topo, but typically it's the least accurate method that we see. Definitely to know your software and have proper SOPs for consistency. Things you have to be aware of are your camera settings. So like your aperture, your ISO value, you have to think about your lighting, shutter speed, things like that. Definitely use a good quality UAV and a camera to get quality data. Always use ground control to validate your data, and that way it's right. And then this is just a quote from one of my colleagues, Bob Green, out in New Mexico, is, with photogrammetry, don't contour the top of hay. It won't get you bare earth. So just keep that in mind. The processing is very computer intensive, but it doesn't require a lot of manual intervention. It's a lot of just click and let it go. And then, what I found out in this process is I say just take it to the cloud. Not only did I get better results, but it was just a lot easier to deal with. I didn't have to worry about it. I just upload it and I get an email when it's done and I bring it in and I can start looking at it. Aerial LIDAR, it was a great tool. It was accurate, very effective. It was easy to use. The quality was better than photogrammetry. As you can see, it wasn't quite as good as mobile LIDAR, but that's no surprise to us. That's about what we expected. If you have an aerial solution, with the right sensor, you can definitely penetrate vegetation, which we saw in one of the slides. A couple of things is just be aware of your area of interest and how you fly it. We had that issue going around the curves where we're missing some data, and then always adjust and validate, your flight with ground control. And then, utilize the power of TBC, not to shamelessly plug TBC, but it really was kind of our saving grace in this project because, any issue that we had that was related to a projection or coordinate system, we were able to figure it out and make it work. So working in local sites, definitely take a look at that. And then the mobile LiDAR stuff, obviously it's not a secret that it really blew us away. It worked really well. It was fast, it was accurate, probably not a feasible solution to use on 1,600 feet of road or even a mile of road. Might be overkill, but definitely in those longer projects, it really shines. You get the added benefit of imagery, and the brunt of the office work brunt of the work is in the office, so it's not dependent on the weather. You don't have to have people in the roadway. And I just want to throw an example here of a project for BP way up in the North Slope in Alaska, more of a real world scenario. They scanned 250 miles of road in about 3.5 days. They had some speed restrictions. They had to stay under a certain, speed limit, but then they pulled out, 613 miles of line work in TBC in about 120 hours. So that's just kind of maybe a large scale real world scenario that you can kind of digest there. All right, with that said, that's a lot of information. Hopefully I didn't go too fast. I wanted to make sure we got right around that hour mark, but it looks like we have several questions here. Dylan and Nathan, hopefully, are you still there?
Yep, still here.
All right, so I'm gonna scroll up and look at some of these questions here. One question was from Phil about the glass beads we use. Phil, yeah, I'll take that offline. I'll send you a link to that. There was a question about the cross sections at 100 feet. How valid will your surface be relative to the LIDAR? So that's a good question. I mean, obviously there's, things that can go on within 100 feet, but I feel like for 100-foot cross sections, that's pretty standard for what we were trying to do to validate our, our accuracy. Our GPS data, we did a lot closer. But even comparing the LIDAR data to the GPS, it really didn't make any difference. 100 feet just is kind of what we chose, and it worked well for us. I don't know, do you guys have any other comments on that? Maybe we should have done them closer, or what are your thoughts?
Yeah, not too much more to add to that other than, the shorter intervals definitely going to give you a better representation of what the road surface looks like. As long as we're comparing apples to apples across the different sensors with our cross sections, I think things worked out pretty well.
Right. And the other thing too is this is kind of a, it's one of those things where when you do it, you end up finding about, oh, we should have done this, we should have done that. So obviously there's other things we could add to it, and we can do that. We might do at some point in time. So maybe going back out with more cross sections is maybe something we can do at some point and see if it changes the results. But I don't expect in this particular situation, just because it's a relatively flat road and not a lot going on, I don't expect it to change much, but it's something we could look at. Next question is in the Dell Air AI platform. I had mentioned that we used a different processing engine. And the question was, which one do we use in the study? So obviously the local photogrammetry that we used was Pix4D. And the Dell Air platform, you have a couple of options depending on what you're trying to do. So you can use the Pix4D engine, which we certainly could have done, but we wanted to do something different. There's also an option to use the Agisoft Metashape engine, and then there's an option to use the Bentley context capture image. And in this particular one, I had used Bentley context capture before, so I kind of knew what I was going to get, but I really had never used Agisoft Metashape. So the Dell Air AI platform we chose Agisoft Metashape was what we used to process that data. Let's see what else we got here. Whoops. If the flight time of the UAS platform better matched the battery life of the LIDAR battery, wouldn't that reduce the total cost or the total collection time? So I think what the question there is, we had to do several flights with the LIDAR, but a good point there is that was due to battery life on the drone. That wasn't due to battery life on the LIDAR. So one thing we didn't cover here is you could also, there are solutions, especially with that yellow scan LIDAR. There's an example, Quantum Systems, they have a fixed wing, that you could put the VX, I believe the VX20, or no, one of the yellow scan systems in, and then you have an hour plus of collection time. So yeah, there's definitely options there, Cliff, and the total kind of factor there is the battery life of the drone is typically the problem. So yes, we could be a lot more efficient if we used a drone that had battery times that were more comparable to the LiDAR. That's definitely correct. The question was, why did you drive the MX9 at 30 miles an hour as the MX9 allows you to drive faster? It definitely does. It's just we were on a street in a business park. I would have loved to, Dylan, you probably would have loved to rip through there at about 50 miles an hour, but it just wasn't something we could safely do. So that's why we did that. And then also in more of a, I don't want to say urban, but urban-esque type setting that we're in, here we don't have any situations where we'd be able to drive any faster. So that's why we chose what we did. There was a question about feature codes. We did use feature codes in the GNSS survey, but even with the feature codes, we still wanted to go back through and make sure all the lines were curving and stuff, and we're having nice curves and things pushed through there. Oh, this is a long one. Let me just scroll down here. So it says, can you speak to the fact that for most projects you will need a ground survey to accompany the remote survey? for culvert signs, utilities, and anything obscured? What is the break point in miles where it makes more sense to use the ground survey for your surface as well as planimetrics? That's a good question. I'm gonna pawn that off on you guys, Dylan and Nathan. What are your thoughts on that, since you have more real world experience with this?
Well, just from me personally, working with the mobile LIDAR sensor, yeah, there's time involved with collecting ground control. There's time involved in the planning of the route and everything, and just making sure that you can drive the route, first of all. But when it comes to kind of where that break point is, um, what I would say, each survey firm is probably going to have a bidding system where they take it either by mile or by block or whatever their scale is, and they have a dollar amount for that. So when you compare approximately how long it would take to do a section of a road, traditionally with the control versus with a mobile LiDAR sensor, it's probably not going to make the most sense on a smaller scale project versus when you start getting into a much longer project where you have 3 to 5+ miles. That's where I've found that the mobile LiDAR starts to make more sense.
Okay, thank you. Yeah, relative cost to achieve each of these results. That is a good question that I'm not sure I can answer, because it could go various ways. I mean, obviously you have, cost of equipment, right? We're talking, we get up into aerial LiDAR, mobile LiDAR, obviously the price tag goes up, the ROI is different. But you also have to factor in, not just equipment costs, but cost to be on site. So the cost per crew per hour. I don't know if I can really answer that question. I don't know, Dylan or Nathan, if you guys have any insight on that, but it's really kind of depends on the situation, I would say. Okay, no comment.
I don't have anything more to add to that one. Sorry,
Okay.
Jay.
Yeah, no worries, no worries. Ballpark figure on various, I'm not sure what that is, but the various methods, including the level of skills required to operate them. So obviously when you're talking, photogrammetry, you have, at least in the United States, you have to have your 107 and some various level of training and ability to fly, drones. That's one aspect of it that translates over to the LiDAR side. In terms of the flight and the data collection, Nathan, with the yellow scanner or the LiDAR, I don't think there's really anything too special you have to know. I mean, if you can fly a drone, you can pretty much fly the yellow scan. It's just basic mission planning and some manual calibration maneuvers, right?
Yeah, you're exactly right. The mission planning's a little bit different, and there's some manual procedures to initialize that IMU. But other than that, you're still mission planning and letting the drone do the flying for you.
Right. So, so the operation of the drones is pretty much consistent. The MX9 honestly is super easy to use. There's a little bit of setup time, but once it's in, it's basically just pushing a button to record and pushing a button to stop record, correct?
Yeah, that's correct. And something I'll add to that is, a lot of people who are doing mobile scanning, this is becomes kind of a niche for them, and a lot of companies that are investing in this type of technology are actually dedicating a vehicle towards their mobile scanner. So it might not always be an hour of setup and teardown. It might just be a matter of 5 minutes or so to set it up. So obviously, with our situation, we don't have a dedicated vehicle, so it does take a little bit more time and knowledge to kind of outfit the vehicle there. And as far as operating procedures, it really is just as simple as hitting a green button and a red button.
Right. Yeah. On our situation, we had to install all the bracketing for the system onto the vehicle and hook up the battery and all that type of stuff. Where if you had a dedicated system, it's basically just putting the MX9 up there, locking it in place and plugging it in. So there's definitely a difference there. One comment, just correcting me or filling in when I was talking about the LIDAR system on the Quantum fixed wing, talking about more battery life and more efficiency. It's the Surveyor and the Surveyor Ultra. It's not the VX series. So sorry if I misspoke there. Question, do you have a cost benefit ratio for the various methods, cost of equipment, time, etc.? I think that kind of goes back to the previous question. Obviously, there are various different price tags and scenarios here and different configurations thereof. There's single laser and dual laser and stuff. So I don't have anything canned or on paper that I can give you, but if you had something more specific, definitely reach out to us on the side and we can kind of take that offline and maybe crunch some numbers and figure that out for you a little bit easier versus trying to kind of shoot from the hip here. And then the last question here, seen black holes and warping of the ortho photo when processing, usually on the vertical edges, building, etc. Even when performing cross-flight collection patterns for added data, your photos seem clean and clear. Did you see any of these types of issues? Yeah, so Sean, I did see that on a lot of the buildings, pretty standard. Obviously, a lot of the focus was on the road, which for the most part looked really good. But when we started looking at some of the buildings, we definitely saw some of those weird swirls along the edges and in the point cloud, some holes in the sides of the building. Now we only flew this as a single grid. One thing that did come up when I presented this one other place was to fly in a double grid. But even with that, I've seen some of those same things that you're talking about there. So definitely didn't come into play here because we're more worried about the road, but we definitely saw that. Okay, that looks like all of our questions. There were some questions about making this available. So what we do with all of our webinars, this has been recorded and we will post this on our survey blog. So it's just frontierprecision.com. I believe it's /blog. So with probably by the end of the week, we'll have a recording of this up there and I'll see if we can put a PDF together of the slides here for you as well. But I don't see any questions up there. So I guess with that, I'd like to thank everybody for attending and we'll talk to you next time.